Hello, good morning to everyone. I am Kumar Singh from IIT Roorkee, and I would like to begin by expressing my sincere gratitude to Professor Sandeep Bhatt for giving me the opportunity to present today. It's a pleasure to share my insight on the topic strike slip fault. Uh, First we discuss about what is the strike slip fault. So a strike slip fault is a type of the fault where the movement of the block is a horizontal and occur parallel to the fault plane. Unlike normally a reverse fault that involve vertical movement, and strike slip fault accommodates lateral displacement due to the horizontal shear stress. And this fault commonly occurs at the transform plate boundary where two tectonic plates slide past each other. Now, on the basis of the motion of the strike slip fault, we also categorize into two types of the strike slip fault: distal strike slip fault and the sinistral strike slip fault. In distal strike slip fault, if we move on the stand on the one block of this in this figure, so if the block moves to the right, so this is the distal strike slip fault. Example San Andreas fault in California. And the second one is the sinistral strike slip fault, in which when we facing the fault, the block on the opposite side move to the left. So, so on the basis of the how the fault is, if the fault is the states as you seen in the diagram, and if the fault is a curve, so on this basis of we also categorize in the strike slip fault. Now, so what is the transfer fault? So transfer fault is basically it is a transfer the displacement between the two extensive layer contested by the means of the stack removal. As you see in this diagram, if you are seen in this half graben is connected by this kind by the transfer fault. As you also see in this also diagram, here we see the two normal fault. These are the connected by the strike slip fault. So this is basically it is a transfer the displacement between the two normal faults. So now what is the transform fault? So transform fault is basically it occurs it is a type of also transfer fault. So transform fault is occur generally at the here we see in the plate margins. So it is basically the mid oceanic ridge. This is connected by the transform fault, and here you also see the volcan to volcanic arc. This is the connected by the transform fault. So this is basically occur at the plate boundary. So now we discuss about the what is the development and anatomy of the strike slip fault. So uh, we we generally discuss about the in this topic riddle shear fault, yeah, arc fracture. So how this is developed. So here we draw the diagram to represent how to the develop to strike slip fault zone. So basically, uh, so this is so so this is a granite rock, and this is a clay layer. So as you know, granite is a hot rock. So in this, if you see, this is the vertical strike slip fault. So due to this vertical strike slip fault, granite is developed brittle shear fault, but due to this uh, clay layer, this is not a brittle, so this is ductile. So here in this we not develop a single type of fault. So here this will create a zone to develop a strike slip fault zones. So like with this strike slip fault zone. So here with this type of the fault it develop, and the exact plane of this fold is like uh, parallel to the shearing direction of this fold. So what we say, when this fault goes into the clay layer, but it is not trace a vertical. So this zone develops certain characteristic feature. Here you see it develop many types of the fold. So this is basically of the, it depend upon the slip amount, and the axial plane of this fold is rotate toward the shearing direction, yet less than 90. If we draw here, we would, so this is the shearing direction, and here if we this rotate, but this is not a 90 degree, this is approx 85 degree. So it is basically total depend upon the slip amount. So now here we discuss about the what is the riddle shear fracture. So for riddle shear fracture we have draw. So this is basically shearing direction. So here we make the strain ellipse. And here is a R1, and this is the R1, and this is the R2, and this is the compression direction. So this R2 is the basically high angle fracture. Sorry, high angle fracture, and this R1 is a low angle fracture, low angle of fracture. So this is the same sense of shear, same sense of shear, or this is generally 20 to 30 degree, and this is the approx 60 to 70 degree. So now we see the different type of the characteristic feature developed by this riddles here. So first we draw the diagram to make clear understanding of this picture. So here we make the better diagram to make clear understand of this riddle shear fracture. So we draw diagram this right lateral strike slip fault. Here is the sense of this here, and we make larger diagram to better visualize this. So first we make to the strain ellipse. So, and this is the two fracture R1 and R2, and this is the compression direction, and this is the extension direction. Okay. Now this is the sense of this here. So this is the sense of this here. Now here it zoom out this R1 and R2. So here this is the R1 and this is the R2. This is the R2 and this is the R1. So and this fracture is there are the two types of the fracture are developing the P fracture and T fracture. So P fracture is basically lower angle in the R1. It is equivalent to the R1. So we have diagram. This is the P, and T fracture is perpendicular to this extension direction. So now T fracture is so basically this is the T fracture, which are the perpendicular to this extension direction. Now we also develop some fold here, and axial plane of this fold is equal. So now equivalent to the R1. Now here in this diagram we also develop some features like thrust, stellolites, and normal fold. So basically thrust is also developed to parallel to this except the fold. So uh, so this is the thrust which is parallel to the axial plane of the fold. Okay. Now the stylolytes is basically developed parallel to the axial plane or generally developed in this limestone. So this is a stylolytes which is also developed to this axial planar fold parallel to the axial planar of the fold. It is basically pressure induced developed by the pressure induced solution in the limestone. And now the normal fault is also developed uh, perpendicular to the stretching direction. So the normal fault is here we denote the normal fault. So this one is the normal fault. And, this. So this one is the thrust, and this one is the stylolites, and this is the fold. And so now many type of the structure are developed. So write one by the one. So first one fold is developed. Fold, and second is R1, which is a basically same sense of the shear, and R2 is the opposite sense of the shear, or P is, it is basically equivalent to the R1, equivalent to the R1, but for the lower angle, as we also discussed in this diagram. And T is, it is basically perpendicular to the extension, and thrust, it is basically parallel to the axial planar of the fold. And stellate, it is also parallel to the axial planar of the fold, and normal fault, it is a perpendicular to the stretching direction and parallel to the this T fractures. This is a T fracture. So, this normal fault is uh, this normal fault is parallel to the T fractures, parallel to the T fractures. So here also in this diagram, this thing, here is also they see the same thing, how the fold is developed, and how is this normal fault and reverse fault also previously I already discussed in this diagram. So now move on to the conjugate strike slip fault. This is a basically developed by pure shear. As you see in this diagram, uh, this is a Himalaya. Basically, this mechanism is known as indicator. So basically, India is moving the northern sides, and when this collide with this China plate, so basically it's developed the strike cliff fault. Some material are extruded away in the northern eastern sides. So and this experiment is described by the Tepinuri in 1986, and basically this developed the two conjugate faults. So as you need in this also this in diagram, this is basically a block which move in the northern side, and when this collides, so some material are the extruded away from this side and develop basically two type of conjugate fault. So now we move on to the next slide. So in this slide we basically discover restaining and releasing bands. So what is this? So in this restaining and releasing band, basically we see some contextual structure including stololites and cleavage and reverse fold and form in the restaining band. And releasing band, as in name suggests, when the sinistal strike slip fault steps to the left and distal fault step to the right. So generally, such a bend produce extensional structure such as normal fault and extension fracture. And this releasing band basin along the strike slip fault are called pull-apart basins. So, as we name suggests, restaining. So restaining, in this we see the contextual structures. And in releasing band, we basically see the extension structures such as normal fault and extension fractures. So as you also seen in this diagram, this is the pull apart basin which is seen in the extensional setting, and in this some formation of this contraction duplex. So in this we also see the formation of this fold in the contraction setting. So here we see an example of the depth valleys. So depth valley is basically type area for the pull apart basin. So in this diagram you see this this is the uh, extension setting. So due to this extension we create in this valley region. So this is death valley region. So this is a basically example of the pull apart basin. So basically, as we discussed about the style slip fault as shear zone, this is not a single plane and not a straight plane. So first we see about what is the overlap. So overlap, basically this is the, if you draw the diagram, this is, so basically this is a overlap, and where in this second diagram we also seen the what is the band. So basically band is in this region we see the band, and this is the sense of the shearing direction. So this is the restraining band, as you see the above slide, restraining band. And another band is, this is the releasing band. So basically this is the releasing band. This is generally done in the extension setting. Extension setting, and this is generally seen in the compression setting. So this is also known by the term transpression. So transpression generally means this include the in this term I already seen, this means trans plus compression, and this is also known as the, due to extension setting is also known as this term by the trans tension. Sorry, trans tension, trans plus extension setting. So in this setting we also see the some uh, some normal fault. Here we see some normal fault, and in compression setting we also do some fold. This is fold. So basically strike slip feature give both strike slip, strike slip give both feature overlap and band. So now, due to this in extension setting, we generally the generate basin, uh, as we see that a pull apart basin and push apart basin. So here we see in the flower structure. So basically in this diagram, as we go to the diagram, there is the widen in this figure as we move to the downwards. So this is basically negative flower structure. So this is basically formed by the uh, due to the pull apart basin. This is as we see in the discussed in the previous slide. Here this is the positive flower structure. This is basically uh, due to form of the de-staining band, and these all structure are the surfacial exposure. So now we discuss about the also the combination of the strike slip simple shear and contraction. So this range is known as a transpiration. Uh, if the combination of the strike simple shear and the contraction, and if the strike simple shear and extension, so there is a combination of this transtension. If there is the no contraction involved, so this is the pure strike slip simple shear, and if there is the no extension involved, so then this is also strike slips simple shear. Now, what is the strength partitioning? So basically, strength partitioning is a it is an internal decomposition of the total strength across a deformed zone into the zone or domain of the different type of the strength. It is basically occur when the different component of the deformation are accommodated by the separated structure due to the oblique plate motion or variation in the rock strength. So in transversion setting, basically style slip motion may occur along the major fault while thrusting happens nearby, and in tensile zone, style slip fault may be associated with the normal fault or pull apart basin. Partitioning can occur as you see in this diagram. So this also occurred the horizontally, vertically, in different depth. It also help in the understanding the tectonic process, seismic hazard, and the also many various process. So these are the my references, and thank you.